I'm standing in northern New Mexico, in the Carson National Forest, east of Farmington, south of Dulce, just a few miles off the western edge of the Jicarilla Apache Nation. On December 10, 1967, 4,227 feet below this marker, a 29-kiloton nuclear device was detonated in an effort to stimulate the production of natural gas. This is the Gasbuggy site. Gasbuggy was the first of 3 experiments conducted by the Atomic Energy Commission and private industry partners, in this case the El Paso Natural Gas Company, to investigate the feasibility of using nuclear weapons for the production of oil and gas. In some senses, the Gasbuggy test was successful. The device detonated, it created a cavity almost 300 feet tall beneath my feet, the cavity filled with natural gas. A new well was drilled from this point directly downwards into the cavity, and over the following 2 years, over 200 million cubic feet of natural gas were extracted. But in practical senses, the test was a failure. The natural gas produced was too badly contaminated with radionuclides to be used. Instead, it was burned off on site from a flare maybe 100 feet behind me. The additional natural gas that was produced as a result of the nuclear stimulation was estimated to be worth about $75,000. To put that into scale, the nuclear device alone had a cost estimated of about $750,000. 2 further experiments were conducted, and although there was some effort toward a large-scale application of nuclear-stimulated natural gas production in western Colorado, ultimately the concept of nuclear weapons for petroleum production was a failure. Today, all that's left of this site is this monument installed by the Atomic Energy Commission during remediation activities in 1978, a few leftover items from the drilling and testing activities, and an open clearing out here in the woods, punctuated by markers indicating the locations of the test wells used for instrumentation. The soil, the surface here is perfectly safe today. In fact, contamination with diesel fuel was a larger concern at final remediation here than radioactivity. But there are institutional controls in place. Institutional controls that specifically prohibit any digging to a depth of almost 4,000 feet from this location, in order to ensure that the nuclear contamination from the detonation remains contained in the cavern below this point.
Project Plowshare, also called Peaceful Nuclear Explosions or the PNE program, was an effort early in the Cold War to identify peaceful, industrially useful applications of nuclear weapons. Plowshare's tests were conducted from 1961 to 1973 in the United States, and the Soviet Union actually had a very similar program at around the same timeline. The politics behind Project Plowshare can be a little bit complex, but the short version is that public apprehension about nuclear weapons and atomic energy was increasing, so there was a perceived need to show the public that atomic energy could be a good thing. At the same time, the enhancements or the developments being made in the design of nuclear weapons caused a lot of optimism, both within the nuclear weapons program and within industry, that they could be used for some sort of useful end. The idea of Project Plowshare was to develop public-private partnerships, programs jointly operated between the Atomic Energy Commission and industry that would evaluate the use of nuclear weapons for industrial purposes. At first, the main application contemplated by Plowshares was essentially excavation. Nuclear weapons could be used to produce big holes. You might be familiar with the Sedan crater, which is probably the most notable artifact of Project Plowshare, a huge crater in the Nevada National Security Site created by a nuclear detonation to demonstrate that it was feasible to dig a large hole with a nuclear weapon. Sedan was conducted in part to contribute to the concept of nuclear bays, the idea that nuclear weapons could be used as an alternative to dredging in order to create navigable bays in areas with otherwise shallow waters. An experiment was planned in Alaska to develop sort of a full-scale version of this concept using 5 weapons, although it was never actually executed. Perhaps the apex of Project Plowshare excavation ambitions was Project Carryall. an experimental effort to use a series of nuclear weapons to excavate a huge cut through the Bristol Mountains in the Mojave Desert that could be used to route Interstate 40 and the Santa Fe Railroad. That was a partnership between the AEC and the Santa Fe Railroad, and, of course, Caltrans. As you might imagine, Project Carryall never happened. There was a lot of public opposition to the use of nuclear weapons at or close to the surface, which created the potential of large volumes of fallout. The focus of the Plowshare project began to shift to underground detonations. Underground testing at this point was in wide use within the Nevada National Security Site, and we were fairly confident that we could conduct underground detonations with minimal environmental impact. The question, of course, is what's the use of detonating a nuclear weapon deep underground? And by far the most promise was the excavation of deep underground resources. Mining had enough difficult practical concerns around it that there wasn't really that much exploration of underground mining, although proposals were developed. Oil and gas was the selected direction of the late days of Project Plowshare.
This structure behind me is the only above-grade feature that remains from Gasbuggy activities. I don't know what it was originally for. I haven't been able to find references to it before the 1978 remediation plan. But the remediation plan notes that it's being left in place for the Forest Service to use to mount an interpretive sign. It's a little amusing that the Forest Service didn't do that. They put the interpretive signs on new frames over there. But it's the most significant thing that we have left of the Project Plowshare's era activities. So to really understand what went on at this site, we have to talk a little bit about natural gas production. I'm far from a petroleum engineer, so take this with a grain of salt, but I'll do my best to explain what was going on here. This part of New Mexico is a very active oil and gas production field, and it was back in the 60s when the project occurred. El Paso Natural Gas operated natural gas wells throughout this region. There's a substantial amount of usable natural gas underground here, but the reserve is what petroleum engineers refer to as tight. That means that there's a lot of natural gas underground, but the rock that it's contained in isn't very porous at all. So there's a lot of static pressure, but when you drill a well and then start extracting the gas, you get very little flow. There just isn't the permeability for the gas to actually flow through to the well. To increase production from tight reserves like this one, drilling companies will fracture. You're no doubt familiar with fracturing or fracking today because of the common practice of hydrofracking, which was a huge component of enabling the enormous natural gas production throughout the Southwest and Texas. Hydrofracking is actually a fairly modern method, though. It wasn't known yet in the 1960s when this project was planned. Instead, the best practice for fracking was actually lowering explosives down the borehole and setting them off. The problem is that boreholes aren't very large. Most gas production boreholes were something like 6 or 7 inch. So there's a practical limit on the amount of explosives that you can lower down the hole. El Paso Natural Gas approached the Atomic Energy Commission with an idea. A nuclear device can put enormous explosive power into a relatively small package. That means that you can get, in this case, the equivalent of 29,000 tons of TNT down an 18-inch borehole. The resulting explosion creates a large void, and the shock wave fractures the rock some distance away from the void. The natural gas then flows into the void and pressurizes it. If you can drill a well down into the void, you should be able to extract that gas at a much greater volume of flow than you would get had you not performed the nuclear stimulation. Or at least, that was the idea.
There were several criteria for locating Project Plowshare tests. Perhaps the most obvious is that they had to be in a fairly remote location in order to minimize the hazard to human health. In the case of the Gasbuggy project, it was located in a fairly sparsely populated part of New Mexico, but nonetheless only about 6 miles away from a village of the Jicarilla Apache Nation. This did lead to some protests, which were dismissed in one New York Times article as being just a few Indians. The Gasbuggy site was located in Carson National Forest, not far south of what was then Highway 17. It's now US Highway 66. The area was undeveloped at the time, although the mineral rights had been leased to the El Paso Natural Gas Company, which was actively exploiting the area. The infrastructure for a nuclear detonation is fairly complex and fairly large, so there's actually a number of distinct sites within the Carson National Forest that were related to Gasbuggy. The most obvious is Ground Zero. Ground Zero is where this video was filmed, and it's the location of the modern monument. It's also the only location that any Gasbuggy equipment was located after infrastructure for the original detonation was removed. There are several other sites of interest, though. The recording trailer park is a little bit to the south, and then further away, the control point from which the test was operated, and a helicopter pad used for getting personnel into the site. To be honest, on this trip, I was running out of daylight, and there was a lot more snow cover than I expected. I'm planning to return later in the year when the snow is melted off to see if there's anything to be seen at the recording trailer park or the control point. But I know that they were graded and reseeded even prior to the primary remediation work in 1978, so I'd assume there's not a whole lot left. If we're real lucky, I might be able to find the remains of some of the cable runs that connected Ground Zero to both the control equipment and the recording equipment. Within the Ground Zero area, oil drilling equipment was used to excavate the shaft for the nuclear device itself, as well as a series of test shafts further out around the area. This diagram depicts the state of the site after the detonation, though, when a lot more equipment was installed in the Ground Zero region. What you see here is actually the equipment used to facilitate the production testing of the natural gas. Natural gas came out of the detonation well itself, labeled GBER here because it had been re-entered. So after the detonation, they drilled a new 7-inch well down the same path that they had originally lowered the weapon down to access the cavity. The natural gas then flowed through a set of equipment which was designed to separate gas from produced water, sort of a normal oil field operation. But it was also used to measure the composition and the radioactivity of the gas. Eberline, a company that I've mentioned in videos before, provided all of the radiation measurement services for the test, and that included a system they called the El Paso Online Monitor that continually measured radiation levels in the gas flowing out of the well. None of the gas produced was sold. All of the gas that was produced on site was burned off at a flare stack, which had both radiation monitoring and a steam treatment system to reduce the amount of radiation that was released into the environment. Of note on the site are also the test wells, 1, 2, which was re-entered, and 3, which was a post-test well. Some distance to the north, well 1036 was a pre-existing El Paso natural gas production well that was shut down and then used for instrumentation during the Gasbuggy test. And to the south, well GBD, drilled for the Advanced Research Projects Agency. Earlier you saw the pipe stanchion, which I mentioned is the only remaining structure from the Gasbuggy operations at the site. That's located right here, along with an unlabeled nearby concrete slab. I really wish I could figure out what they were used for, but it's nice to know that there's something original still in place. The decontamination pit was used both during the drilling stage, but especially during remediation of the site, to wash radioactive particulates off of the equipment that was used. I looked around to try to find evidence of that decontamination pit. I know the area was graded and seeded, so there likely isn't much to see. Especially under snow cover, I wasn't able to pick out anything. I really like this artist's illustration of the Gasbuggy Ground Zero equipment. You can see here the derrick that was used for drilling the well and was also used for lowering the weapon in. They actually had to put this in place, remove it, put it back in place. They went through several cycles so that they could access the hole from above with the crane as needed to actually put some of the equipment into it initially. Nuclear weapons for underground tests have to be lowered very deep beneath the ground, and that produces some real practical challenges. At the Nevada National Security Site, there's a history of different methods that have been used for actually lowering the weapon. In the case of the Gasbuggy test, they assembled the nuclear device with its environmental control unit in an assembly building. They picked it up with a mobile crane, and then they lowered it into the borehole on a metal frame that hung it just below the surface. They then attached a drill string pipe, the same type used for drilling wells, to the top of the nuclear device, and they actually used their standard drilling equipment to lower it down the well on a drill string. That's a somewhat different method from what was normally used at the Nevada National Security Site, when they would lower the weapon using a mobile crane in steps, adding another length of cable on each time. In the planning documents for the Gasbuggy test, the Lawrence Radiation Laboratory, which is now, of course, Lawrence Livermore National Laboratory, said that they felt that for future tests, the process could be optimized by building a large capstan winch that would allow the weapon to be lowered on a steel cable in one step. As far as I know, they never developed that system. Another important feature at a nuclear test site is the recording equipment. There is a lot of instrumentation in the borehole with the nuclear device itself, in other boreholes drilled for that purpose, and surrounded throughout the area, including seismometers placed as many as miles out. The recording equipment was placed in a set of semi-trailers at what they called the recording trailer park, in another clearing a short distance away. The recording trailer park isn't far enough away to receive no shock force, but it is much reduced. At the Nevada National Security Site, a somewhat more complex design was used to further isolate the recording trailers from shock, but it seems like in the case of the Gasbuggy test, they didn't actually do that much. They were mostly just semi-trailers parked. The report notes that upon re-entry about 3 hours after the detonation, there was some minor damage to electronic equipment in the recording trailer park, but nothing too severe. The control point where the operators were located was quite a bit further away. It's actually fairly close to a present-day campground in Carson National Forest. This is a great view of the test package itself. Now, the nuclear device is contained in this cylinder, but much of the cylinder is actually the environmental control unit. Remember that electronics design wasn't that sophisticated in the 1960s, and nuclear weapons were difficult to get to work in the first place. The temperature down at the bottom of the borehole was something like 125 degrees, sometimes observed as high as 140, and that was well above the temperature range that the nuclear device itself was rated for. So one of the most important purposes of the environmental control unit was actually to refrigerate the weapon. Once again, there have been different approaches used over time, sometimes surface refrigeration equipment to pump chilled water or glycol down the borehole. In this case, in part to try to reduce costs, a fully self-contained refrigeration system was used. So there's a refrigeration cycle, air conditioner essentially, in this environmental control unit that exchanged heat with the fluids, the water that was already present in the well. One of the other functions of the environmental control unit, in this case, was also to provide protection from the ground pressure deep in the well. Now, the well casing should handle that pressure. There was some concern that with other pre-detonation activities going on in the area, including drilling other boreholes, there could be at least a partial collapse of the liner of the main borehole. So the environmental control unit was designed to withstand the full ground pressure at the weapon emplacement position. One of the more interesting things you'll see here is the cable itself, which was used to connect the whole test package to the surface. This cable used a fairly novel design that contained everything within one assembly that was just taped to the drill string and affixed with clamps as they lowered it down the borehole. That was a lot simpler than the method that was typically used for tests at the Nevada National Security Site, where there were a large number of cables that they had to manage all the way down the borehole. What we see here is the device as it was being lowered by a mobile crane into the borehole. It was hung just below the surface at this stage so that the derrick could be reinstalled over the borehole and then used to lower it to its final depth on the drill string.
The main borehole at this site is identified as GBE, or more practically Ground Zero. It's 30 inches near the top, but most of its length is a 20-inch casing. It's also referred to as an 18.25-inch well. I assume that's the usable interior area of that 20-inch casing. The nuclear device itself was lowered over 4,000 feet down that well at the end of a drill string. But that wasn't the only equipment on site. A set of smaller wells were drilled to a similar depth so that instrumentation could be placed close to the nuclear device when it detonated. To my right, well GB2RS. The R indicates that this is a re-entry well. Well GB2 was drilled as an exploratory well before the nuclear device was installed, to a depth of 4,247 feet. The force of the detonation caused much of the well to collapse in on itself. It's a re-entry well in that after the test, they re-drilled it to the same depth. This well was used to install a set of instruments at different elevations in order to measure the shock force and displacement that resulted from the use of the nuclear device. After the detonation, it was used to collect samples to investigate the extent of the fracturing, as well as the extent of the radionuclide contamination underground. Walking around the site, my husband noticed this multi-core cable. There's, it seems like 4 pieces of it sticking out of the ground near borehole GB1. I can't be sure, but it seems like there's a decent bet that this cable connected some of the instrumentation that was installed in the borehole, or some type of other equipment on site. It may have run through conduits to the recording trailer park, some distance to the south of here. Borehole GB1 is marked by this metal post to my right. During the main remediation activities here in 1978, a few years after experiments ended, all of the boreholes on the site were closed. In most cases, that means that the lower part of the borehole was filled with grout, a concrete plug was installed about 600 feet below the surface, and then the borehole was filled with mud up to the top. These markers were installed so that the boreholes could be located again easily if necessary. GB1 here ran 4,300 feet deep in a 2 3/8 inch casing. This well was used, like the other boreholes around the site, for shock instrumentation and radiation measurements after the test. This well wasn't re-entered, meaning that the well was drilled before the test, and then to the extent that it was usable, it was used after the test for sample collection, but there was no post-test drilling in this location. Very close to borehole GB1 is borehole GB3. GB3 is sort of the opposite. It's a post-shot well. This was drilled entirely after the detonation on the site in order to facilitate sample collection. GB3 ran to 4,809 feet deep, making it one of the deepest wells on the site. There's another instrumentation well that's a little different. Some distance this direction out in the trees is actually a natural gas production well, which was drilled by the El Paso Natural Gas Company before the test was ever planned. I assume that their operating experience with that well was part of why they selected this site for the nuclear fracking experiment. In 1978, the El Paso Natural Gas Company, as part of the remediation activities at this site, transferred ownership of that well to the Department of Energy. It wasn't used for natural gas production during the test, but it was used for instrumentation. And it could now be considered one of the test wells on the site under DOE ownership, although it's got an older history than the rest of the artifacts that you see here. Finally, there was a 5th well worth mentioning. Up the ridge into the trees was well GBD. Well GBD was drilled by the Atomic Energy Commission on contract for the Advanced Research Projects Agency, which later became DARPA. ARPA used the well for their own set of experiments. I've had a hard time finding details on those experiments, but I think they were related to the propagation of seismic shock waves as a result of a deep underground nuclear test. That was an area of research of great interest in the 1960s because nuclear tests were increasingly being conducted underground. So, from a non-proliferation perspective, the best way to detect nuclear tests by other countries stopped being satellites and started being the observation of the seismic waves that can propagate a substantial portion of the way around the planet after a nuclear detonation.
3 hours after the detonation, AEC personnel re entered the site to inspect the results. Although there was a substantial shock at ground level, damage to the wellhead equipment was actually fairly minor. No radiation was observed at the surface, although during removal of the wellhead equipment, there was some radiation detected. It seems that gases produced by the detonation had actually worked their way up the instrumentation cable and were trapped inside between the pairs. That was allowed to dissipate, and there was no risk to the personnel. Borehole GB1 contained a particularly interesting instrument. An electrical cable was suspended down the full length of the borehole, and time domain reflectometry was used to detect any damage or fractures in that cable. The shock wave should propagate from the bottom of the borehole towards the top, because the bottom of the borehole was at about the same elevation where the nuclear device was installed. As a result, they can visualize the arrival of the shock wave in the breaks in the cable caused by the shearing of the rock at different heights. As you can see, the cable remained intact at about 3,800 feet. That's one of several data points supporting the top of the cavity created at between 3,800 and 3,900 feet. Shortly after the detonation, they began the process of re-entry, meaning that they drilled a new borehole down the route of the original borehole used to emplace the weapon. Eventually, at about 3,900 feet, that borehole broke through to what they believed was the cavity resulting from the detonation. At that point, they began instrumenting the borehole to measure the pressure of the gas produced, and ultimately to extract gas from it. Keep in mind that this test was performed in December, and much like the site was when I visited, weather was cold and wet. They faced a number of struggles in this testing because of the conditions, particularly with some of the gas handling equipment repeatedly freezing up. They suspect that this led to some inconsistencies in the pressure and production data that they collected. This figure shows measurements from the first and second test production runs. Specifically, they're showing the pressure of the natural gas emerging from the well as it was extracted. As you can see, as gas flows out of the well starts to essentially empty. The pressure throughout the cavity lowers. The initial high pressure reflects what had built up, and the lower pressure at which production settles should indicate the rate at which new gas from the reservoir is actually infiltrating into the well. A third, longer production test run was performed just a few weeks later, although it was complicated a bit by weather conditions as well. That run showed similar pressure readings to the previous. Attempts were made to use the pressure curves derived from these tests to characterize both the size of the cavity and the amount of gas that could now infiltrate into it. Because of some combination of the cold weather and the unknown behaviors of this new nuclear fracturing technique, they had a hard time drawing hard conclusions from these numbers. A short report summarizing the testing that was performed in the year following the original detonation highlights some of the tension that existed over this project, something that sort of presaged the whole lifespan of oil and gas stimulation experiments with nuclear devices. The Lawrence Radiation Laboratory seemed skeptical that the method was effective, but El Paso Natural Gas remained optimistic. Of course, one of the most interesting questions with the nuclear stimulation of oil and gas production is the radioactivity problem. Radiation and production measurements from the original 1968 runs didn't really give enough data to make strong conclusions, so experimenters returned in 1973 to perform some much larger production runs. There's actually a little bit of inconsistency around the record here. You might remember I said earlier that around 200 million cubic feet of gas were produced. I actually should have said closer to 400 million cubic feet of gas. It's surprising how quickly you run into errors like this when you're reading historic materials. A little over 200 million cubic feet of gas was produced during the original 1968 test run. During 1963, almost 200 additional million cubic feet of gas were produced. That brings us to a total of 393 million cubic feet produced, 319 million cubic feet of which was marketable hydrocarbon materials. The radiation properties of the gas were interesting. Experimenters weren't sure how this would actually work out, but they thought that gas that spent a long time in the cavity area would develop radiation contamination, but gas that flowed into the cavity from the reserve through the fractures created should be relatively free of contamination. That meant that when you first started flowing gas, it would be fairly radioactive, but with time, the radiation levels would drop as you got to gas that had spent less time in the cavity. Data from the experiments generally supports this theory, but it's not quite the success that you might have hoped for. They estimated that about 60% of the gas produced during the 1973 test runs was new gas from the formation. That gas showed about 35% lower radioactivity than gas that had been extracted from the cavity initially. The experimenters noted that the radiation levels in the gas extracted during 1973 were actually fairly similar to the predicted radiation levels for gas extracted from the planned Western Colorado project. That gas had been approved by the EPA for distribution to customers. But there was a lot of political opposition to the distribution of radioactive gas. I think especially since, due to the natural gas economy of the time, that would have mostly been marketed in California. Widespread public opposition to the idea of radioactive gas arriving at the stovetop in your home seems to have been one of the big factors that ended nuclear oil and gas extraction experiments. Of course, this all might leave you with a question. Is drilling for natural gas with nuclear weapons a good idea? Well, there are two basic problems with the proposal. The first is radiation, and the second is money. As for radiation, the natural gas produced by these wells is contaminated with several different radioactive gases, gases that aren't easy to separate from the natural gas product. The AEC contended that the danger of radioactive natural gas could be addressed simply by diluting it into natural gas produced by other methods to lower the radioactive content to an acceptable level. The El Paso Natural Gas Company was a little more political in its approach to the question, saying that they assumed some technology would be developed that allowed for removal of the radioactive contamination. In any case, the idea of natural gas contaminated by tritium and krypton seems to have been the end of nuclear oil and gas as a popular idea. The second question, that of money, wasn't so thoroughly addressed by the Plowshares project, but we can take some estimates from the article Project Gasbuggy and Catch 85, written by Peter Metzger for the New York Times, February 22nd of 1970. Metzger says that the AEC estimated in a public information meeting that the nuclear explosive cost about $750,000. Drilling costs for the emplacement well and the cement to backfill it, about $754,000. Redrilling to re-enter the cavity, $230,000. Indemnification for damage to nearby property, $62,000, and with interest charges, he estimates the total cost of the effort at about $3 million. And that's not including the experimental costs of the Gasbuggy shot that drove the prices up to closer to $5 million. Considering that $3 million investment, what is the value of the effort? Over 10 years, it's estimated that the nuclear fracturing technique at the Gasbuggy site would have enabled the production of about 500 million cubic feet of natural gas above what was produced by similar wells nearby, done without the benefit of a nuclear explosive. The market value of that gas? About $75,000. Improvements in technology and the method of nuclear fracking were assumed to drive the cost down and the benefits up. But still, analysis performed by the Department of Energy well after Project Plowshares estimated that nuclear fracking as a concept could probably only produce oil and gas that was worth 10 to 20% of the cost of the operation. Ultimately, and probably fortunately, nuclear fracking just doesn't seem to be economically feasible. So, what came of the Gasbuggy site? Extraction experiments were performed primarily in 1968 and 1973. Pressure monitoring of the well continued for several years after 1973, but by 1978 the decision was made to decommission the site. This corresponded with the end of oil and gas stimulation experiments and effectively the end of Project Plowshare. The helicopter pad, control point, and recording trailer park were remediated sometime after the original detonation. By 1978, they had already returned largely to their original condition. What was left for environmental treatment was the Ground Zero site itself, which contained both the boreholes and the equipment that was used for the gas production experiments. Perhaps the most complex problem to solve from an engineering perspective were the boreholes. You can't really leave an open borehole around. Water flowing both up and down the borehole tends to create contamination problems, and that's all the more so since the lower ends of the borehole here were likely exposed to radiation and contaminated beyond acceptable limits for human exposure. All of the smaller test bores were remediated using a fairly similar method. The bottom part of the shaft, closest to radioactive contamination, was filled with concrete and grout. Water was then allowed to fill the borehole until about the 600-foot level, where a concrete plug was installed. That corresponded with a fairly hard rock formation and made a good place to seal the whole thing off. The borehole was then allowed to fill with some combination of water and mud again, until another concrete cap was installed close to the surface. The sites of the boreholes were returned essentially to their original condition. The only thing left today are the markers that were installed to relocate the boreholes later. The main shaft itself was addressed with a similar method, but of course it's quite a bit larger. A huge volume of concrete was flowed down the well to fill almost the entire thing. That process was somewhat complicated by the fact that the casing had been damaged in a number of places, so they had to flow concrete specifically into those areas to ensure that the casing was well sealed around the grout placed around the outside of the well. At the top of that shaft, a steel plate was welded over the top of the casing, which I think, if I can interpret this diagram right, was about 3.5 feet below the surface. Finally, it was backfilled with soil and seeded, and then the monument that marks the site today was placed directly on top. The big question with environmental remediation of any nuclear site is always radiation. Now, keep in mind that the vast majority of the radiation involved in this experiment was trapped in the detonation cavity far below the surface. The contamination concern at ground level was a result of the gas that had been brought up itself. All of the equipment that was used to handle the produced natural gas was steam cleaned to remove particulates and then surveyed for residual radiation. Most of that equipment, once it was found to be clean, was actually returned to the El Paso Natural Gas Company to be reused on other sites. Some equipment couldn't feasibly be cleaned. It was shipped to the Nevada National Security Site where it was buried in a radioactive waste landfill there. The liquid that came from the steam cleaning process, as well as removed from some of the equipment, was mostly injected right back down the main borehole before it was sealed, basically putting the radiation back with the other radiation 4,000 feet underground. Some wastewater from the cleaning process was produced after they had sealed the borehole. That wastewater was actually evaporated away using the steam generation system that was already on site. This sounds a little questionable, and by modern standards it is, but to be fair, in 1978 it was approved by the New Mexico Environment Department. Following this radiation cleanup effort, a survey by Eberline found that radiation levels at the site were acceptable for release to unlimited use. This was effectively the end of radiation cleanup activities at the site, and the Department of Energy considered it remediated after 1978. That held out until the early 2000s when another type of contamination became a concern. During the 1960s, it was a fairly common practice to mix diesel fuel into the drilling mud that was used. It provided lubrication and a bit of a solvent benefit. Of course, we know today that diesel fuel is actually a fairly substantial environmental contamination concern problem. And indeed, sampling performed in the early 2000s found that hydrocarbon contamination from diesel fuel in the mud settling pits at the Gasbuggy site was a major concern. High levels of residual hydrocarbons were found in the soil across large areas, which basically reflected everywhere that drilling mud returning from the holes had flowed. In 2004, a remediation contractor returned the site to address this problem. Almost 5,000 cubic yards of soil, everything that was found to be hydrocarbon contaminated, was dug up and shipped away to a hazardous waste landfill. I included this figure from a 2004 remediation report because I enjoy every opportunity to look at ground-penetrating radar data. Now, if you're looking at this and thinking that especially that lower figure doesn't depict much, well, the experts agree with you. The contractor, a company called Sunbelt Geophysics that performed a survey to identify underground features, was able to locate a lot of leftover piping and cabling. That probably includes the wires that we found on site. But they weren't able to find the grout layer that they were looking for at the bottom of the settling ponds. They think that the water-saturated soil just attenuated their radar equipment too much, and they were only able to penetrate a few feet. After the 2004 cleanup, the site was submitted to the New Mexico Environment Department's Voluntary Remediation Program. That application was accepted, and the site is now considered fully remediated. There is no hazard to human health or to the environment at surface level, and the site has been released for unlimited use, primarily because of its location in a national forest as a recreational site. Of course, environmental remediation always includes some combination of physical cleanup and institutional controls, policies and rules that ensure that radiation or other contamination that has been contained stays contained. And the Gasbuggy site is indeed subject to institutional controls. No drilling or digging is permitted deeper than 1,500 feet down to a level of about 4,500 feet within a fairly large radius of the Ground Zero site. In the case of Gasbuggy, those institutional controls are fairly easy to enforce. As part of its contract with the Atomic Energy Commission to support the tests, the El Paso Natural Gas Company transferred all of its mineral rights for the PLSS section containing the test site to the Atomic Energy Commission. The Department of Energy still has exclusive ownership of the mineral rights today and uses them to ensure that no one else drills in the immediate area. I hope you enjoyed learning a bit about the Gasbuggy site. Despite its remote location, it's actually one of the most accessible nuclear testing sites in the United States. The Trinity site is only open 2 weekends a year. The Nevada National Security Site tours have to be scheduled far in advance, and even then they can be tricky to get. The Gasbuggy site is just there, about 8 miles south of Highway 64. As you head southwest on Highway 64 from Dulce, where I assume you were visiting the Scientology Mesa, you'll take Indian Service Road J10 to the south, which is just before the end of the Jicarilla Apache Nation Reservation. That Indian Service Road turns into a Forest Service road, and that will take you straight to the Gasbuggy interpretive site. Those roads are in good condition. You'd have no trouble in a passenger car in good weather. Even in poor weather, I don't think it would pose much of a challenge. But the access roads to some of the outlying sites, like the Recorder Trailer Park, didn't seem very passable in the conditions there right now. I'm hoping to return in a few months when the snow has melted off to make a more thorough inspection of Ground Zero and to take a look at the Recorder Trailer Park and the control point. I don't think there's much left to see at those sites, but I'm hoping that maybe with the help of a metal detector I can find some remains of the cables that used to connect them to Ground Zero. Most of the information in this video comes from technical reports of the Lawrence Radiation Laboratory. Those are available from the Defense Technical Information Center. Other information comes from reports on the Environmental Remediation Program. Those are mostly available from the Department of Energy Office of Legacy Management, although some older documents are also held at DTEC. Of course, the most important artifact of the program is the site itself, maintained by the Jicarilla Ranger District of the Carson National Forest. There is another notable Project Plowshare's site in New Mexico, Project Gnome. I hope to visit Project Gnome, perhaps also sometime later this year. In a 1967 planning document, Lawrence Radiation Laboratory engineer Wayne R. Woodruff wrote that the nuclear operation I have outlined here is fairly simple and straightforward compared to some of the more complex activities we've undertaken elsewhere. However, it is unique here in its application. Project Gasbuggy is indeed a unique part of our nuclear heritage and of the history of the Southwest, yet it is little known. Contemporary reporting on Project Plowshare is riddled with errors and inaccuracies. I've seen a surprising number of different figures for the amount of gas produced by the Gasbuggy well, for example. One of the wrong ones slipped into this video. I've even seen one article that I'm pretty sure just has a typo in the number they give. It matches the one in a Lawrence Radiation Laboratory report, except for one digit. The most significant one, of course. Even the yield of the nuclear device is contested. From the documents I've read, I believe it was planned as a 26 kiloton nominal yield, but 29 kiloton was the measured yield of the actual detonation. These kinds of things stack up over time, so take this as a reminder that sometimes the best sources are the ones that come with an apology note from the Defense Technical Information Center that it is scanned from the best available copy. Until next time, don't forget to like, comment, and subscribe, spay and neuter your pets, courage.